Yes, so good morning, students. Welcome to this session of work, power, energy. Okay, so quick review of the aspects of work, power, energy that we have learned till now. So, for example, we started with the definition of work done by a force. So, in general, work done is defined as integration of F dot ds from initial to final position. This is called the path integration. But specifically, it becomes F dot s if the force is constant. Then we saw the concept of conservative and non-conservative forces. So we saw if the work done is path independent, okay, or if the work done in a round trip is zero. That means that the force is conservative. Example of that being spring force, gravitational force, okay. Any constant force these are all examples of conservative forces. Yeah, this is the closed integral, so it's work done in a round trip. Okay. Similarly, if work done is path dependent or work done in a round trip is not equal to zero, that means the force is non-conservative. So an example of that is friction, kinetic friction. Okay, so this is about conservative and non-conservative forces. Okay. Now, next thing we saw was the concept of potential energy. Okay, and relation of potential energy with the internal conservative force. So we saw that potential energy for a system is defined in such a way that change in potential energy is negative of work done by internal conservative force. So whenever a system has internal forces which are conservative, we can define potential energy for the system as the energy associated with the state of the system or the configuration of the system, such that change in potential energy is equal to negative of work done by the internal conservative force. So having defined the potential energy like that, next thing is we define the work energy theorem, where we say that work done by external forces plus work done by any non-conservative forces equals to the change in kinetic energy plus the change in potential energy for a system. Okay. So again, if work done by external forces is zero and work done by non-conservative forces is also zero, that means change in kinetic energy plus change in potential energy is zero, or the sum of kinetic energy plus potential energy is constant. So for a system where this thing happens, we say there is conservation of mechanical energy, because the sum of kinetic and potential energy is called the mechanical energy. Now, as far as potential energy is concerned, two specific examples is potential energy of a spring, which is defined as half kx square. So change in potential energy of the spring is defined as half k final position square minus initial position square. And the other example is the gravitational potential energy, where if a body of mass m is given a vertical displacement of delta y, the gravitational potential energy, yeah, k is the spring constant. Yes, Smith, you are familiar with springs by now. Yeah. Delta y in this formula is the vertical component of displacement. Yeah, non-conservative forces includes the work done by friction, kinetic friction. Okay, so this is a quick recap of the concepts that we have learned till now. Okay, so let's start with simple application example. Okay, so suppose we have this situation So this is a rough surface with coefficient of friction 0.2 and the mass of this block is equal to 10 kilograms. Now initially it is at rest at time t equal to 0. But what we now do is we are applying a horizontal external force on it. So from t equal to 0 onwards, the block is pushed by a horizontal external force F such that F equals to 25 plus 5s, where s is the magnitude of the block's displacement in meters. F is the force in newtons. Okay. So calculate the speed of the block at a displacement of 2 meters. Okay, so let's understand how we can do this question very easily by using work energy. So as the block is moving at any point of time, when its displacement is s, what are the forces acting on it? There is the external force, there is normal reaction, there is mg, and there is kinetic friction mu n. So here work done by normal reaction is 0, work done by mg is 0. Work done by F we will calculate by integration F ds, because it's a variable force. It's a variable external force. We'll calculate this way. Work done by friction will become minus mu mg s. Okay. So this is the non-conservative force. So since there is no conservative force at all, okay, so there's no concept of potential energy here. So when we apply work energy theorem, in general, we will say work done by external force plus work done by non-conservative force is change in kinetic energy plus change in potential energy. This term is 0 because there is no conservative force term acting over here. This is the work done by F. This is the work done by friction. Okay. So ultimately, we'll have the equation that work done by the external force F plus work done by friction is equal to the change in kinetic energy. And the block started from rest initially. Okay, and after some time, it has a speed v. So our equation will become, now this thing will become how much? It will become 25s plus 5s square by 2. So 25s plus 5 by 2 s square. Whereas this thing will be minus 0.2 into 10 into 10 into s. So minus 20s is equal to half mv square because the initial speed was 0. So this is our formula. Becoming finally half mv square is equal to 25 minus 20, that is 5s plus 5 by 2 s square. Yeah, so let's calculate. Now we want to calculate the speed at the instant when v is 2 meters. Okay. So at s equal to 2 meters, so very simple answer, 2 meters per second is the speed. Okay, next example. Okay. So as you can see, the section of the horizontal track EB is rough, and the rest of the track is smooth. So a block is moving at speed v naught at the horizontal track before the point A as shown. So first of all, find the minimum value of v naught so that the block may reach the point C. And second part, if v naught is half of the minimum value of part 1, then will the block cross the point B? And if so, up to what height will it climb on the curved section after B? Okay, so just try this out. This is a typical example of application of work energy theorem. So here what you can do is you can take your system as the block plus the Earth's gravitational field. So in this case, what is happening, that mg will become your internal conservative force. Okay. Friction will be your non-conservative force. Okay. and work done by any external force is 0. Because there's no work done by normal reaction. Remember, in a situation like this, normal reaction does 0 work. Yeah, mass of the block is not given, interestingly, and you will not require the mass, because when you write the equation, m will cancel out on both sides. Yeah, you can take the value of G as 10 meters per second square for this. Okay. All right. So here, if we apply the work energy theorem, overall, we will see that if we are assuming that the block goes from the initial position all the way up to this position C, so starts from here, then goes through the rough patch in between, emerges here with some velocity v prime like this, let's say, and then reaches all the way to this point C, where this height is h from here to here, whereas the rest of the track is again smooth. So this part had a coefficient of friction of 0.4. Okay. So from the initial position, let's say O, to this position C, if we take a system as the block, let's say mass m plus the Earth's gravitational field, okay, we can say that the work done by friction will be equal to the change in kinetic energy plus change in gravitational potential energy, because there isn't any work done by external force. Okay, work done by friction is the work done by non-conservative force. Okay, like this. Okay, so work done by friction here will be kinetic friction from A to B only. Okay, so that is just going to be minus mu mg into that distance d, where this distance is b. Whereas change in gravitational potential energy will be mgh, because we are applying this all the way from the initial position O to the top position C. Now the condition for it to reach C is that it should not stop anywhere before. No? It should have velocity all the way up to this point. Okay. So the condition is that the speed at C should be greater than equal to 0. Okay. This is the condition to reach the point C. So the limiting condition which corresponds to minimum V naught to reach C is that V is just about equal to 0 at the point C. So it just momentarily stops at the point C, reaching that point. That is the limiting condition. Okay. So we apply this limiting condition. We have work done by friction minus mu mgt is equal to change in kinetic energy, that will become 0 minus half mv naught square. Okay. Plus change in gravitational potential energy mgh. So we have the condition that half mv naught square should be equal to mgh plus mu mgt. In this case, we'll get the v naught as the minimum speed, such that the block just about reaches the point C. It does not stop anywhere before C. Because final kinetic energy is 0, the initial kinetic energy is half mv naught square. So the change is negative, na beta? Kinetic energy is not negative. It's the change in kinetic energy which is negative. Kinetic energy cannot be a negative quantity. But the change in kinetic energy, if the kinetic energy is decreasing, that will be a negative quantity now. So you can see that change in kinetic energy is final kinetic energy minus initial kinetic energy. So the final kinetic energy we are taking as 0 because V is 0 at the point C, and the initial kinetic energy, because V is equal to V naught at the point O where it started the motion. Okay. So anyway, so from this you can see that V naught will come out to be square root of 2gh plus mu gt, or we can write this as square root of 2g h plus mu t. So we can solve this now. 2 into 10, h was how much? 10 meters, and mu was 0.4, and d was 20. Right, these were the values. Yeah, d is 20, h is 10, and mu is 0.4. So 6 root 10 meters per second. This is the minimum speed. Just about reaches the point C. Okay, so take this down and now work out the second part yourself. Find out what's happening to the block if V naught is half of this minimum value. So if V naught is 3 root 10 meters per second, then find how far will the block go. Does it cross the point B? If it crosses the point B, how far up does it go on the curved incline? Okay, so just work this out quickly, people. Take this down and work out the second part yourself. Yeah, so it does not cross. Very good. Okay, so it will stop somewhere before B. So we can see here that this distance being 20 meters. Okay, if this is given an initial speed now of 3 root 10 meters per second and mu is equal to 0.4. Now, if we assume that the block has come out on this side, okay, then half mv square minus half mu square should be equal to minus mu mg t. Okay, so half mv square minus, okay, this should be equal to minus 0.4 m into 10 into 20. Okay, so cancel off the m. So you'll get v square by 2 minus, this will become how much? 90 by 2 is equal to minus 200 into 0.4. So that's 50. So we'll get v square by 2 is equal to minus 50 plus 45, which is a negative quantity. So that is not possible. Okay, so therefore we can see that the block does not cross the point B. Okay. So instead the block comes to rest somewhere before here only. It comes to rest somewhere over here, and let's say this distance is x. So what will happen is that minus mu mg x will be equal to 0 minus half m u square. So mu mg x will be equal to half mu square, or x will be equal to u square by 2 times mu g. So 3 root 10 whole square by 2 into 0.4 into 10. So this distance x we'll see will become 90 divided by 8, isn't it? So x will become meters. So it will stop within the rough part at a distance of 11.25. Yes, Devansh, that's correct. Yes, exactly, Durgesh. We can do that. If we assume some height h or something and we solve for h will come out to be negative, which is not possible. Okay, next up, let's look at an example involving a spring mass system and also gravity. Okay, so suppose we have a smooth tabletop like this. Okay. So if the block had not stopped, na, Shikhar, then we would have just applied work energy, the same equation we did earlier. Okay. But H would be the variable. Understand? Suppose what was happening is that it was going up to some point like this. So at this point, C V would become 0. And in between, we have the rough part here of distance D. So we would have applied work energy from this point to this point, where this would have been some unknown height H. So H we would have calculated. So work done by friction would be change in kinetic energy plus change in gravitational potential energy. So minus mu mg would be equal to minus half mu square plus mgh. So here h would be what we would find out. So as you can see from this, we would have got h as u square by 2 minus mu gd divided by g, or u square by 2g minus mu d. This would have become the value of h. Okay. But as it turns out that if you substitute the value of u as 3 root 10, then this h will come out to be a negative quantity, which is not logically possible. So that is what is telling us that it's not going here, it's stopping somewhere between a and b. Is it clear, Shikhar? Okay. Now let's come back to this question. This height here is h. So now the block, okay, is not attached to the spring. Mass of the block is 5 kilograms. The spring constant is, let us say, 20 Newton per centimeter, and h is equal to 5 meters. Okay. Also take g as 10 meters per second square. Okay. Now initially an external agent pushes the block through x equal to 5 centimeter against the spring, that is compressing it through 5 centimeters. And releases the block from rest. So first of all, find the block's speed of projection from the tabletop. Okay, so the block will get projected from here and then come and hit the ground somewhere here. So find its speed v just before impact at the floor below. So again, both the parts you can do by work energy, even though the second part you know how to do by application of projectile motion, but you can just do it by, yeah, Samarth, in the previous question, it does not cross the point B, na beta? It stops before it reaches the point B. It stops within the rough section only because it doesn't have enough kinetic energy to come out of the rough portion. Okay, so let's look at the solution of this. So see, first part, what we can do is we can see that as the system is going from a state of compression of the spring, okay, so here x naught is whatever 5 centimeters and u is 0, to a state where the block loses contact with this spring, okay, and goes to this. So what is happening? Change in kinetic energy plus change in spring's potential energy should be 0 for going from here to here. Okay, so half mu square minus half kx naught square should be 0. So you will get as x naught square root of k by m. So that is 5 centimeters converted to meters into square root of, now this was how much? 20 Newton per centimeter. Okay, so 20 Newton per centimeter we will convert to SI unit. So it will become 2000 Newton per meter, and mass was 5 kg. So 2000 Newton per meter divided by 5 kg. So U will become 5 into 10 raised power minus 2 into 2 into 10 in meters per second. So U is becoming how much? 1 meter per second. This is the projection speed from the top of the table. Okay. So next you will see that when it goes from this part to this part, okay. So for the second part, change in kinetic energy plus change in gravitational potential energy should be 0. So half mv square minus half mu square minus mgh, because it's coming down through a vertical height of h, this should be 0. This is really very simple. V square will become u square plus 2gh. So V will become square root of 1 square plus 2 into 10 into whatever height I had given. So this V will become square root of 101 meters per second. So nearly 10 meters per second. Very close to 10 meters per second. Slightly greater than 10. So as you can see, this type of question is very simple application of work energy theorem. The conservation of mechanical energy is happening. Let's look at another example of a spring mass system. Now this time we have a vertical situation like this. Okay. So initially there is an external agent who is applying force from below such that the block is at rest in equilibrium, but the spring is in natural length. So K is given to us as 15 newtons per centimeter. The mass of the block is 2 kilograms. Take G as 10 meters per second square. Okay. Now initially the block is held at rest with the spring at natural length by the application of this external force. Okay. Now at t equal to 0, the external force is withdrawn. It's removed altogether. So the block starts falling. So first of all, find the speed v of the block as a function of its displacement. X. Secondly, find the maximum speed V max in meters per second during its downward motion. And third, find the maximum extension of the spring. x maximum in meters, sorry, in centimeters. Okay, so just try this out. So the first part should be very easy. Just apply the statement of work energy theorem. Make sure you understand what kind of system you should take so that the statement of work energy theorem is easy to write. Then from analysis for the first equation, we will understand how to find out Vmax and also the maximum displacement x. Okay, so let's start with the first part. So this is the initial state of the block from where you are releasing it. Okay. But the difference is now you are just removing this external force. So it's starting from the rest position, but it starts with not from equilibrium, but rather with a large value of acceleration equal to G, because the spring force is 0 right now. Now, after some time, if it comes to a situation where the block is displaced by X, so the block has gone down by displacement X. So the spring is now stretched by X. And by now the block has a speed V in the second diagram. So comparing the two diagrams from here to here, you can see that if we take a system as the block plus the spring plus the Earth's gravity, okay, there is no external force. There is no non-conservative force. So mechanical energy is conserved. Both the spring force and the gravitational force are internal conservative forces. So mechanical energy is getting conserved. Okay. So for this system, change in kinetic energy plus change in the spring's elastic potential energy plus change in gravitational potential energy should be 0. So going from here to here, the kinetic energy is changing from 0 to half mv square. So positive change. The spring is stretching from 0 to x, so plus half kx square. But the object is going down through a displacement x, so minus mgx is equal to 0. So very simple relation. So from this you can see that v square is equal to gx, or rather 2gx minus k by m x square, or v as a function of x is like this. So this is the first part's answer. The speed of the block as a function of its downward displacement x becomes like this. Okay, now for the second and third part, what we have to understand is that the general motion of the body, for the second part we want to find out the maximum speed, and third part we want to find out the maximum extension of the spring. So what we have to understand here is that the block will oscillate vertically. Okay, so what will happen is that it will have maximum speed at the mean position. Okay, so mean position is also what we call the equilibrium position. So I'll explain, just give me a bit of time. And the maximum displacement will be when the block is at rest momentarily at the lowest point. Okay. So the oscillation of the block is going to happen in such a way that when the block starts from here at x equal to 0, it sets off with an acceleration g. Okay. So after some time, it's here. Now it still has a velocity like this and it still has an acceleration like this, because what is happening here, mg is still greater than kx. Okay. So at this point of time, mg being greater than kx means the block is accelerating. Okay. Implies that the block is accelerating downwards. So that means speed is increasing. Okay. But as that happens, next stage, it reaches a situation where at some point of time, kx becomes greater than mg. So that point of time, it starts decelerating because still it's on its way down. Okay. So when kx becomes greater than mg, the block starts decelerating because the acceleration is upwards. So speed is now decreasing. Okay. But in between this position and this position, where the acceleration is upwards and the acceleration is downwards, it also, just for an instant, it passes through what we call the mean position, where the acceleration is 0. It passes through the mean position of the oscillation, where for a moment, kx is equal to mg. So this is the instant at which the speed is maximum. This is your maximum speed, because going from here to here, okay, what is happening? Speed is increasing, but the moment you cross this point now, your speed starts decreasing. Okay, here speed is increasing. Okay. And like that, this continues till you reach that lowest point, where momentarily what happens, your speed becomes 0. But you have a strong upward acceleration. Okay, so this is the lowest point, or it is the extreme position of the oscillation. Okay, and from there the block will continue upwards. So we'll understand this with another set of diagrams in detail, but first just understand this point here, that why the speed is becoming maximum at the mean position, because going from 0 to mean position, mg is dominating over kx, so the speed is increasing. And the moment you cross the mean position, kx dominates over mg. So again, it starts decelerating. So पहले accelerate कर रहा है, बाद में decelerate कर रहा है. So that means at the position where you are just about switching from acceleration to deceleration. So momentarily your a is 0. That is the instant when speed is maximum. Okay, so this is how top to bottom of the vertical oscillation looks. Then again from the bottom position, it will accelerate upwards, come up back to the top position, and then repeat the whole cycle. All right, so the oscillation of the block is something like this. Starts from x equal to 0, u equal to 0, but with a strong downward acceleration of g. From here, it's going to this in-between position where x is such that kx is less than mg. So it has a downward acceleration. And by now it's developed some downward speed also, v. From this, it goes to equilibrium position where kx has become equal to mg. So for a moment, its acceleration has become 0. But at this particular moment, its speed is maximum. Okay. Then it continues from that point. So now what has happened? Kx has become larger than mg. So it's decelerating even while it's going downwards. And decelerating, it reaches some kind of position where the speed becomes 0 for a moment. And at that point of time, your x is the maximum x. Okay. Now from this, it will go back to this position where it's going up with some acceleration upwards. Okay. Then again comes to mean position. So this is when acceleration again becomes 0, but the speed is maximum. So this is a position where kx is equal to mg. And then further up, till at some stage it reaches the mean position. It reaches the x equal to 0 state. Okay, where again its v becomes 0. So it has the maximum downward acceleration of g. And then the whole cycle repeats itself. So this is the oscillation cycle. Okay. So this is the oscillation cycle in which this is one extreme position, the top one. This is one extreme position at the bottom of the oscillation. And then again, this is back to the extreme position at the top. Okay. So extreme position is where v is 0 and acceleration is maximum. V is 0, the acceleration is maximum. Again, v is 0, the acceleration is maximum. Whereas in between, this is the mean position. And again here, this is the mean position. So at the mean position, what is happening? Your speed is maximum and acceleration is 0. Again here, your speed is maximum and acceleration is 0. So it keeps going up and down in oscillation, where every time on its up and down journey, as it passes the mean position, its speed is maximum. Alternately downwards and upwards, but its speed is maximum. Whereas at the lowest point, the speed is 0. Okay. So from work energy, we had the relation that in general, half mv square was equal to mgx minus half kx square. So from this equation now we will find V is equal to V max at equilibrium position, equilibrium or mean position. So mean position or equilibrium position is the position at which acceleration is 0. That means kx should balance mg. So that is how we will find the answer to the second part. Whereas x will be equal to maximum when v is equal to 0. That is at the lowest point, at the lowest extreme position of the oscillation. Okay. So what we have to do is now we have to substitute this. Okay. So for the second part, for v equal to v max, substitute acceleration as 0 or kx equal to mg. So x should be equal to mg by k. So how much was that now? 20 divided by 50 or 0.4 centimeters. So substitute this x in this equation. So half mv max square is equal to mg into 0.4 centimeters minus half k into 0.4 centimeters square. So from this we will get our V maximum as square root of 2g into 0.4 centimeters minus k by m into 0.4 centimeters square. Now k by m, you'll remember, was k was 50 Newton per centimeter. Okay. So we will substitute that in Newton per meter. Divided by mass was 20 kgs, I mean 2 kgs. Into 0.4 into 10 raised by minus 2 square. So this value of V that we'll get, this is nothing but our V max. So this 0.2 meters per second will be our maximum speed. Yes, that's correct. Okay. Whereas for the third part, what we'll do is we'll just substitute v as 0. So x is equal to x maximum when v is equal to 0. So half mv square, which was mgx minus half kx square, should be 0. So this should be 0. So x equal to 0 we won't take as the root because that's the initial position. Whereas x equal to 2 mg by k, this will become our maximum extension. So x maximum will become twice the weight, so that is twice of 2 into 10 divided by the spring constant. We can keep in Newton per centimeters. Okay. So that's becoming 40 by 50. So 4 by 5 or 0.8 centimeters. This is the maximum extension. Now you can see something interesting. The maximum extension is exactly double of this value. Equilibrium is at 0.4 and maximum extension is at 0.8. Now that is not surprising at all because it's an oscillation. So there is symmetry. So if this was your x equal to 0, this is x equal to 0.4, this is your equilibrium position or mean position, and this is your x equal to 0.8. This is again the extreme position. So always when this kind of an oscillation happens, this is equal to this. A is called the amplitude of oscillation. So it's not surprising that this is double of 0.4 because from the top extreme to the bottom extreme, the displacement has to be double of the amplitude. So that is double of the displacement to the mean position. Okay. So this is a slightly more advanced type of application of work energy where we are understanding the properties of a vertical oscillation using the work energy theorem in terms of the maximum speed and the maximum displacement. Okay. So we'll discuss more about this type of situation tomorrow. But yeah, for your test coming up on Sunday, you have to revise up to the concept of conservative, non-conservative forces and potential energy. Basically till what we had done in the last lecture, that is lecture number 4 of work energy. Okay. And of course, make sure that you are competent with friction and Newton's laws type of questions also. Okay. So that's it for today's class, people. We'll continue with this discussion tomorrow.